use of conditional probability, sort of condition on the, if you are able to condition on the right event, then you can compute the probabilities of certain complicated events. All right. Okay. The final topic is Bayes' theorem. And I will give an example of it used to, as I mentioned, that Bayes' theorem can be used to refine your initial hypothesis when new evidence is found. Okay, so let's look at in those terms. If I write P of H as probability of say a belief or a hypothesis being true, and let's say we have some new evidence. So one would like to compute or refine our hypothesis based on new evidence. So evidence E. So this is our posterior probability of hypothesis being true given new evidence. Right. And then the flip probability of E given H is what we'll call the likelihood. So how likely is the evidence given our hypothesis? So how likely is our evidence given the hypothesis? Okay, so we have our elements to state Bayes' theorem. So Bayes' theorem says the following. Probability. So we are interested in the posterior probability because we have some prior belief about our hypothesis or a prior probability, let's say distribution of our hypothesis. And we want to update our distribution or belief by new evidence. So this is the Bayes' theorem says okay, so that is our Bayes' theorem, except that I can, and of course we need probability of E to be greater than 0 over here. But we can actually refine it by using the law of total probability. I can write P of E as so here I'm just writing the law of total probability. So here H complement is the alternative hypothesis. Okay, so that is our Bayes' theorem. So the idea of Bayes' theorem is that in trying to sort of update our hypothesis. So let's see how we can give an example or a scenario where this can be used. So scenario. Okay, so we are trying to, so we are a pharmaceutical company and we are trying to do a clinical trial of a new drug that we are developing. So there is a new drug and we are trying to find the efficacy of a new drug. Interested in finding the efficacy of a new drug. Okay. And we have some prior belief of the efficacy of the drug based on similar drugs or opinions of experts. So let's, so DE stands for drug efficacy. And we believe that the drug efficacy is going to be high with probability, let's say 0.8. So this is our prior belief of the drug being highly effective. And then we go into clinical trials. So let's say we do some clinical trials. And we get some data. So we have some clinical data. And we have the probability. So how likely is the clinical data given that our assumption of the efficacy being high? Let's say it's 0.7. And the likelihood of that kind of clinical data, given that the drug efficacy is low, is, let's say, 0.6. Okay. So we are given this information. The first is our belief that the drug has high efficacy, is 0.8. And then after the new evidence, which is via clinical trials, we have this likelihood. How likely is this data given that the drug efficacy is high? We have certain probability of that, 0.7. And how likely is the data given the drug efficacy is low, is given by this. So if we apply the Bayes theorem, so we want to know, so what is the new hypothesis about our efficacy given the clinical data. Okay, so now we apply Bayes theorem. Applying Bayes theorem is equal to, so this actually in the Bayes theorem, the right hand side flips. So this becomes CD given DE equal to H. And then on the denominator, we get this term and then the complement of that also. So this is CD given DE equal to H, probability of DE equal to H, plus CD given D. It's the complement of this event, which is efficacy is low. Okay, so let's put in the values over here. This is our likelihood that that the data is such given the drug efficacy is high. This is 0.7. This is our prior belief, which is 0.8. And this is again the same term over here. Plus this is going to be is it 0.6 into this is 1 minus 0.8, so this will be 0.2, right? So this is going to be 56 over 56 plus 12, that is 68. And this is going to be 23 over 34, which is approximately, I think, 0.82 something. Okay, so now with the new evidence, our belief has been updated. Our prior belief was that the efficacy of this drug being high is 0.8. New belief is 0.82. So we've gone up a little bit, and so we have more confidence about the drug now. So one way to use that is that we can go to the next stage of the clinical trial, and then if it sort of keeps on going up, we can go do sequentially, and we can update our belief. Okay, so that's the Bayes theorem. So now let me just summarize what we did. So let me just write the summary. So we want to find out if two events are related, and we want to find the conditional probability of event A given B. And this we found to be probability of A intersection B over probability of B. This is by looking at the reduced sample space. We looked at some examples. The particular case was the two dice with the conditional probability of the sum being 4, or the multiple of 4, or sum being multiple of 3. And then we looked at the law of total probability. So probability of H is equal to probability of H given E plus into probability of E plus probability of H given E into E complement into probability of E complement. And then finally, we looked at Bayes' theorem and gave example. So Bayes' theorem, this is law of total probability. This is definition of conditional probability. And then Bayes' theorem says that if I have a certain hypothesis and we have some new evidence, then the probability of the hypothesis given new evidence is this likelihood function, which is how likely is the evidence given the hypothesis into probability of over probability of plus probability of the evidence given the alternative hypothesis times probability of. All right, so this is our summary of conditional probability and Bayes' theorem. And in particular, Bayes' theorem is a very useful theorem for to do hypothesis, building evidence, and so on. Okay, thank you so much. We'll end here.